Well, Newton, did you manage to make your gravitational telescope to see behind a wall?
It did not work.
Okay, don't worry. Now let's further unravel the mysteries of gravity with a concept of gravitational waves.
You mean I can sum up my surfboard on these gravitational waves?
Don't be silly, Newton. Well, anyway, what is gravitational waves?
No idea. Tell me.
You see, we have shown that massive objects bend space-time, right?
Yep.
Okay. So now imagine that you are this massive object and you quickly and accelerate through space-time. Since we know that a stationary massive objects cause bending and distortion in the space-time, what will happen when this massive object accelerates through space-time?
I don't know. It causes creases in the space-time fabric.
Newton, you are actually right.
I am?
Well, in a way, you see, just like if I have this ball and I push it with increasing speed across this fabric, you can see that it causes creases on this fabric. Now I can show it better if I just drop this metal object on this, and you can see ripples moving out from this metal ball. Can you see that? Let's try that again. So these creases or ripples are what we call gravitational waves, and it actually moves away from the source and travels to space at the speed of light.
Okay, so what is so special about these gravitational waves?
Indeed, you might be interested in this. You see, as the gravitational waves pass through matter, it actually contracts and expands the matter. So, if a gravitational wave is passing through you right now, Mr. Newton, you will actually be taller one moment and then shorter in another moment.
Well, I just want to be taller and not taller than shorter.
Well, at least you can be momentarily taller than
Are
me.
you sure there are really gravitational waves? What is the proof?
Well, scientists are actually detecting these gravitational waves, for example, at the LIGO observatories in the United States. So far, they are able to prove the existence of several gravitational events. Such as those caused by colliding black holes. Now keep your fingers crossed for more gravitational events to come.
Keep your eyes peeled to the channel for our next video on black holes.
So yes, even though you can't ride on your surfboard on these gravitational waves, these celestial waves are indeed extraordinary. The acceleration of massive objects through space causes creases or ripples in the space-time fabric. Now these creases or waves travels outward from the source, which are these massive objects, at the speed of light. What is more amazing is the effect of these gravitational waves on matter. As the waves passes through matter, it actually causes matter to increase in size and decrease in size, corresponding to the movement of these waves. But these changes are so tiny that you need an extremely sensitive senses to detect. So far, we are only able to detect supermassive objects causing these events, such as the collision of massive black holes. Gravitational waves observatories, like the largest one at LIGO, which stands for the Laser Interferometer Gravitational Wave Observatory, are able to detect these tiny changes. Detection requires extremely precise engineering with a precision of 10 to the power of minus 19 meters, or 1/10,000th of the width of a proton. It comprises two enormous laser interferometers, LIGO Hanford and LIGO Livingston, located 3,000 kilometers apart, and two research centers at Caltech and MIT. Now these two interferometers are so far apart to cancel out the Earth-based vibrations so that the actual gravitational waves can be detected and separated from these local vibration noises. Now, how do interferometers work? It uses the physical properties of light and of space itself. Now let's go into more details. The first concept is the constructive and destructive interference of waves. Now, when wave collides, they combine or cancel out each other depending on how the two waves meet. If they are in sync, the two waves add up and the waves gets bigger. This is called constructive interference. Now, when the waves are out of sync exactly, they cancels out each other and the waves disappears. This is called destructive interference. Now, in real life, the waves will add and cancels at various levels depending on how in sync or out of sync they are. So there will be partial constructive or destructive interferences. The second concept is that gravitational waves affect space. Now, when gravitational waves goes through space, it will stretch space in one direction and compress space in the perpendicular direction. Hence, each interferometer's arm is designed to be perpendicular to each other to maximize the difference in lengths of the tubes that the laser will travel. So this is how the interferometers work. A laser light is sent to a mirror that will split the light into two light beams. Each beam goes into separate perpendicular vacuum steel tubes or arms which are 4 km long each. At the end of each arm, the light is reflected back and these two beams will be detected back at the beginning of the arms by a photodetector. If there is no gravitational waves, the two arms are at the same length. Then the two beams received would have traveled the same distance. They will then arrive at the photodetector perfectly aligned. Hence, the lasers cancel each other in destructive interference, and no light is then detected. If there is gravitational waves, the two arms are of different lengths. Then the two beams received would have traveled different distances. They will then arrive at the photodetector out of alignment. The lasers then arrive in various alignments and can have total destructive interference, total constructive interference, or partial interference as the two lights goes in and out of alignment. Hence, there will be flickering of the light as it goes through the gravitational wave cycle, and we see anything from no light, brighter light, and anything in between. This is how gravitational waves are being detected.